Welcome to Ask and Learn.
So in this case, we have this cantilevered bar here with some kind of elastic, let's see, some kind of sphere on the end of it for whatever reason. And then this wall here is oscillating, so it's shaking. So this is kind of like again a base excitation. So this shaking is going to start the shaking, and we want to see how that gets transmitted. How, the amplitude here, does it get amplified or does it get attenuated? So an equivalent system to this is this, right? So instead of basically this bar here, this beam acts like a spring that's then attached to ground. And we can figure out what the spring constant was because we know that we get a static deflection of 14 millimeters when we put 18 newtons of load on the end. So that tells us that our spring constant, our equivalent spring constant for this beam here, is 1,286 Newton per meter. Now, our equation of motion is, I think I forgot to write in K here. So we can just draw a free body diagram here or here, and then we'd have kind of a shear force here. Either way, we get my double dot, where y is y is going to be measured from the static equilibrium of this. So if this were not shaking and if we had gravity acting, again, I'm not sure even if this is supposed to be in the horizontal plane or the vertical plane. But if we had gravity acting, then y would just be a measure from where the equilibrium position is. So we have my double dot plus ky equals delta naught, the amplitude of this, times k times sine capital omega t, where this is the time-dependent part of this base excitation. We're told m was 4 kilograms. Given now we have k, we can get omega n, and that is 17.9 radians per second. We are told that the forcing frequency is 2 hertz, which is, we need to convert to radians per second for our formulas, and that's 4 pi radians per second. And then we were told that the amplitude that this is moving up and down is 15 millimeters. So we wanted to figure out the maximum amplitude, or the amplitude of vibration of this this ball about equilibrium here. So how far does it move up and down? And we can see that that amplitude is just the coefficient in front of the harmonic term in our particular solution. And we know this, and we know this is the forcing frequency divided by the natural frequency. So this is, this is roughly what, like 12. So when we plug this in, what we wind up with is 29.5 millimeters. So we can compare that to this, which is 15 millimeters. So what's happening here is that we're getting kind of semi-close to the natural frequency here. So as this moves up and down 15 millimeters, this is moving up and down about 30 millimeters. So we're amplifying the motion that we had here over here.